Hi there! Welcome to the 26th episode of the Synth project, where we are going to build a synth together. In this episode we are going to build the ADSR module presented in the last two episodes. We will see how the panel of the module looks like and how the various components need to be mounted on it. Special attention is needed for connecting the jack sockets, in particular those for the gate and the trigger inputs, which need to be wired together through the switch embedded into the trigger socket. Before diving into the subject, please take a moment to subscribe and to click on the bell to activate the notifications if you haven't done so already. This way you will not miss any of the future episodes of this series. And now let's begin! Here is the PCB obtained from the schematic we examined in the previous episode. It is full of components and requires two layers to complete all the connections. The 3310 IC sits right in the center of the PCB and it is surrounded by four more ICs, providing all the op-amps necessary to complete the circuit. On the top and the two side edges you can see the space for all the connectors to the front panel wiring. The PCB assembly is done the usual way. First mount the mechanical components, the IC sockets and the connector sockets. When installing the IC sockets, pay attention to the notch indicating pin 1, which needs to be aligned with the corresponding symbol on the PCB silk layer. When installing the connector sockets, pay even more attention with their orientation. Try to orient them all the same way with respect to their pin 1 to assure consistency when you build the corresponding cables. The power connector instead needs to be oriented so that the plus 12 volts is on the correct side. Use the sockets on the synth rack power bus as a reference point, along with the information printed on the silk layer. Orienting this socket the wrong way will damage the semiconductors on the PCB when it is powered up. Next we mount all the resistors. I used a tool I 3D printed by myself to bend appropriately all the leads of the resistors. Once the resistor leads are inserted in the PCB holes, bend them a little bit on the opposite side of the component, so that when you put the PCB upside down to solder them, they will not fall. After all the resistors are mounted, proceed with the capacitors. Insert their leads to the appropriate holes and solder them on the opposite side. And last, remove the excess lead, which should have been done as well for the resistors. Once all the passive components are mounted, mount the diodes. Be careful not to heat them too much or they will melt on the inside, causing the circuit to malfunction. On the other hand, use enough heat to make good soldering points, otherwise over time the diodes will disconnect, causing again the circuit to malfunction. And don't forget to orient them correctly. Finally, insert the ICs in their sockets, orienting them so that their notches are located on the side of the socket notches. To test the circuit on PCB, we need to provide the gate and the trigger signals and verify with the oscilloscope that the correct envelope is generated. To generate at will the two signals, I created a small circuit like the one described in this diagram. Switch S1, along with the resistor R2 of 100K, is used to generate the gate signal. Such signal goes up every time we close the switch by pushing on it, and goes down when the switch is released and opens. The trigger signal is generated out of the gate signal simply by extracting the signal through capacitor C1. Resistor R1 is used to discharge the capacitor once the gate signal goes away. And here is the PCB sitting on the workbench with all the connections ready. These are the 5 potentiometers to control the attack, decay, sustain and release, along with the overall amplitude of the envelope, or peak amplitude. The power supply socket is connected to the piece of breadboard to the right, to which all the alligators from the power supply unit are connected. This one on the right is the circuit we just described, which is supposed to generate the gate and trigger signals and is connected to the corresponding sockets on the PCB. The output from the PCB, which provides the envelope signal, is connected directly to the oscilloscope probe. Look how the red LED turns on every time I push the button on the test breadboard. That is the LED that will be mounted on the panel, which in fact turns on during the whole duration of the attack interval. Note how the LED stays on for more or less time, depending on how I set the attack duration with the corresponding potentiometer. Let's now take a look at the envelope signal of the oscilloscope. As soon as I push the button on the test board, we can see the attack interval, then the decay, the sustain period, which keeps going until I release the button, which is also when the release interval begins. Let's do it one more time. Here is the attack, the decay, the sustain, and the release. So, it looks like the test was successful, and therefore we can move on and work on the module case. Since an envelope generator can be used heavily in a synthesizer, and since it is a circuit that doesn't take much space, I decided to put two ADSR units in the same module and to organize the panel like they were two units side by side. With that in mind, this is what I came up with. On the inside there is a space for two independent PCBs, situated side by side on the lateral panel. Here you can clearly see the holes for the screws that will hold them in place. On the front panel, the two ADSR unit controls and jacks lay vertically side by side. On the top there are the holes for the 5 potentiometers to adjust attack, decay, sustain, release and peak. And then there is a hole for the attack LED, and below it there is a 3 pair of holes, 1 pair for the control voltage output, 1 pair for the gate input, and 1 for the trigger input. Why pairs? Well, for the control voltage output, it often happens that you want to control with the same envelope generator a number of other modules. Having two identical CB outputs help on that, without having to put together extra modules just to duplicate signals. Similar explanation goes for the gate and trigger signals. It is very common that one uses the same gate signal, for example, to control multiple modules at once. It is useful then to be able to bring the signal to one module and have there the capability of pass-through, so that the same signal can leave the module to reach another module. I'm not talking about serial connections of the gate and trigger signals. Rather, the same signal goes through the panels of different modules, totally unaltered, so that it can reach many of them at the same time, provided that each of these modules has a pass-through connector, of course. It is basically a parallel connection, although it doesn't necessarily seem so from the picture. Here is the module case that just came out of the 3D printer. You can see here the panel with all the holes for the controls, the LEDs and the jack sockets. These are the holes to screw the module to the synth rack, and these are the holes to attach the two PCBs to the side panel, like this. It looks like I made a mistake. Yeah, I didn't space correctly the holes on the panel. Well, what I can do now is to drill new holes and leave alone the wrong ones. To mark the position of the new holes, I'm using one of those already there as part of the new set of holes, and adjust the PCB according to it. I will also fix the file for the 3D printer in case I will need to print more cases, and of course, to give you the correct version of it, assuming you will use my same PCBs and rack design. Okay, the new holes are now done, and they match the corresponding holes on the PCB. Good. It is time now to paint the front panel and attach the decals to it. And talking about decals, here is what I have prepared for this module. On top, a description of the module, which is a dual module like we said earlier. Then the graphics for the potentiometers to control the various parts of the envelope and the peak. Then the graphics for the LEDs, and finally the graphics for the jack sockets. We have a double output for the control voltage of each envelope generator, and we have the inputs for the gate and the trigger along with the corresponding pass-through connectors. I will now pause this video to do the painting of the panel, and then I will attach the decals printed out of this file. Here is the painted panel. We can now begin to position the decals on it. First we need to cut the parts of the paper that we don't need, and then we will attach the rest on the panel. Before going any further, let's check one more time that the holes on the panel match exactly the decals on the paper. To help on that, I used an LED lamp from the back and shine its light through the panel holes. Well, it is about right, but just to make sure everything is aligned, I am going to cut the paper in 3 pieces regardless. And now it is just a matter to wet the paper by submerging it in water, then put the plastic sheets on the panel, making sure that it is correctly aligned, and slide the paper support out, removing the air bubbles and the excess of water. Once the decals are applied, we need to wait for the water to dry out, and then we will spray some transparent paint on the panel to fix the decals and to protect them from scratches and the like. And unfortunately things didn't go well with the paint. I did the paint job in the garage and the temperature was very low, around -9 Fahrenheit. Yeah, you heard right, -9. Look what happened to the paint and how the red of the text spread all around on the panel. At this point, rather than scraping everything out and reapplying decals and paint, I will print a new module case, and so I can get rid also of the errors on the side panel. Never apply paint when it's so cold. The paint will not dry out quickly, and it will cause all these issues. Skipping ahead in time, here is now the new panel, with the decals on it and the paint applied at a more reasonable temperature. Finally, the module case is ready. Next step is to apply the copper tape on the back of the front and side panels to protect the circuits from EM interference and to guarantee a good ground contact for all the metal bodies of the components on the panel. Apply the copper tape first to the side panel and then complete the job applying the tape to the back of the front panel. Make sure that there are no bubbles underneath the tape or it can be scratched away very easily. Using a piece of cloth helps in doing so. And now it is time to clear the front panel holes. A very good tool to clear the holes is a thin and sharp hobby knife. Clear the holes first from the front side, removing the extra plastic from the decals. Then remove the copper from the back side, both the parts that cover the holes for the PCB screws and the ones covering the front panel holes. Once all the holes are cleared, we can start applying all the components to the front panel. Start with the potentiometers. Since the wiring is not the same for all of them, I labeled each potentiometer on the back to make sure I put each one of them in the right place. Be careful not to scratch the panel while tightening the nuts. It helps to put a washer in between the panel and each nut. The washer will stick to the paint, and the nut will slide on top of it without destroying the panel. After the potentiometers, attach all the jack sockets with a similar procedure. All the jack sockets are the same, but those for the trigger. The ones for the trigger, and in particular the one for the trigger in, needs to have a switch in it to disconnect the trigger in from the gate in when a jack is inserted in the trigger socket. And here is the front panel fully assembled. At this point we can add the knobs to the potentiometers, making sure they are correctly aligned with the drawings on the panel. This time I have chosen the same red color for all the ADSR controls, and I used instead the yellow color for the PIC controls. To install the PCBs, we need to first mount 4 brass spacers on the PCB themselves, one for each corner. Do that for each of the 2 PCBs. Then we have to position the PCBs on the side panel and use screws to attach them. Unfortunately, the space I left on the side of the front panel was not enough, and the PCBs touch the front panel components. Another mistake on my part. Yeah, I had to use a drill to make new holes. Again. At least now I am finally able to complete the mechanical assembly of the module. I will also have to fix the 3D print files one more time. Nonetheless, I can now move to the electrical connections between the components and the PCB. As I already mentioned, the trigger jack sockets are different from the other ones because they have an embedded switch that allows me to disconnect the internal connection between gate and trigger inputs when a jack is inserted in the trigger input sockets. Here is the diagram representing how these connections are supposed to be done directly on the panel. The gate in and gate through jack sockets are represented by the 2 arrows on the left side. The trigger in and trigger through sockets are represented by the arrows on the right side. Gate in and gate through are directly connected to each other, same with the trigger sockets. The connection between the gate inputs and the trigger inputs are done, however, through a switch, which is the one on the trigger input. This way, when there is only the gate jack connected to the panel, its signal is automatically connected also to the trigger input. But when we insert also a jack in the trigger in socket, the switch is opened, and so the connection between the gate and the trigger sockets is severed. At this point, gate and trigger can be controlled by two independent signals. Let's start by connecting together the two control voltage outputs for both the ADSR elements. Once again, I have chosen to have two parallel outputs so that the same envelope generator can control two different devices at once, if needed. We just need to connect the live connectors. Ground is automatically connected through the copper tape, layered on the surface of the panel. Then we can connect the gate in and through together, and repeat for the second unit. For the trigger, we need to locate the correct pins on the socket needed for the connections. This one on the opposite side of the long prong is the actual jack connector. This one on the side is the pin of the switch. This other one on the opposite side, connected to the center of the socket, is the ground pin. What we need to do now is to connect the main pins together, this one and this one. The trigger in is toward the outside of the panel, the trigger through is toward the center of the panel. So first let's solder a wire between the main pins of the two trigger sockets, and repeat for the other unit. Second, solder a wire between the gate input and the switch connector of the trigger in socket, and repeat, of course, for the other unit. Now we need to attach the cables I previously prepared with connectors for the PCB at one end. The loose end is the one that goes to the jack sockets. All the cables I prepared are done the same way. I used a dark color, blue, for the ground wire, and a light color, white, for the live wire, the one that transports the signals. We need to solder a total of 6 cables, 3 for each unit. There is 1 cable for each pair of sockets. Last thing left is the 2 diodes, 1 for each unit. Just insert them in the corresponding holes in the panel and glue them from the inside. I used hot glue to do that. Last thing to do to complete the assembly is to connect all the cables from the panel to the PCBs. Make sure to connect each cable on its right socket on the PCB. Start with one side of the panel and one PCB, and then repeat for the other side of the panel and the second PCB. Finally, use zip ties to group nicely together all the cables. That will also help in increasing the robustness mechanically, so there will be less chance that cables break or that the connectors detach. So here is the system under test. Everything is already connected. The power supply on the back from there. And this is the upper PCB, which is controlled by the left side of the panel. And on the panel we have already the output connected with the oscilloscope right there, and also we have the gate input, which comes from our well-known now push button, which is powered through the same power supply as the upper blade. So let's run the test now. Let's zoom in the oscilloscope. With all the controls in this position, you see the attack is almost to the max, same for the decay, sustain is about half away, and the release is almost 3/4 of the way. The attack is to the max, so we can see better what's going on, but we can change all those parameters as long as we run the test. And so here is the first shot. Let's push the button, and here is the attack. There is lower now. This is the decay. This is the sustain, and finally the release as soon as I let go the push button. There it is. Now let's change some parameter. For example, I'm gonna move all the way to the left the attack control, like this. And let's see what is his effect on the output. And here it comes. You can see the attack is instantaneous, then we have the decay, the sustain, and finally the release. Let me do it one more time, and I'm gonna play with the sustain so you will see how the level in the middle changes, reducing it or increasing it. And the release. Okay, let's run some further tests. I have changed again the parameters, so this is now. Let's bring to 0 the attack, and yeah, now it's disappeared. Now let's bring to 0 the decay, and there it is. And now let's bring to 0 the release. Let's see, now it's basically a regular square wave. The initial attack is really brief, and then it goes away. But if I bring to the max the sustain, then it's gonna be basically exactly like the shape of the trigger. Okay, now let's test the other ADSR module, and let's see how that one behaves. Okay, I have moved the power supply to the other module now, and I have moved also the connectors of the output on the right side and the gate input on the other side. So now I can play with this one. Right now all the controls are set to 0 besides the sustain that is set to the max and the peak is set to the max. So let's see what happens now on the oscilloscope here with these settings. So let me push the button, and basically it behaves like a regular gate. Now I'm gonna add some attack, just a little bit, and let's see how it behaves this time. Still very brief. Let me increase it more substantially so we can look at it better. See, now it's more visible. Let's increase it a little bit more. There we go. Let me decrease the sustain so we can see the difference. There we go. Let's decrease the sustain a little bit more. Okay, again. Attack, decay is quick, sustain, and release is also quick. So now let's increase the decay. And let's see how it behaves. Attack, decay, sustain, and release is still fast. Let me increase the release too. And now let's do again the trick. Attack, decay, sustain, and release. Perfect. So this one works too. It's now time to install the module in the rack. I have decided to put this module all the way to the right in the lower shelf, so it is close to the keyboard and the slider controllers. So I'm now punching the holes for the screws. I'm connecting the power supply cables to the module, one per PCB. I'm connecting now the other end of these cables to the power bus in the rack. And now I'm positioning the module case. And finally adding the screws. To test the module, we will have to do some patching with the VCO and with the keyboard controller. We will start with a simple and standard configuration controlling the envelope of the VCO with the ADSR module. We first connect the CV output of the ADSR to the volume control of the triangle wave of the VCO. Then we connect the CV of the keyboard controller to the VCO to be able to control its frequency. And now we need to connect the gate output of the controller to the gate input of the ADSR module. Let's keep the peak to the max for now. I'm beginning to test setting all the ADSR controls to 0, with the exception of the sustain that is set to the max. This way we should have an output just like we are used to. And here it is. So it is basically like there was no envelope generator connected. Now let's increase the attack. And let's also add some decay. Decrease a bit the sustain so we can feel the effect of the attack and the decay. And I am leaving the release to 0 for now. Since I don't have the way to keep around the keyboard signal after I release the key, the release has no effect right now. To make the release meaningful, I will have to add to the synth yet another module, a sample and hold circuit which will remember the value of the last control voltage generated by the keyboard and will keep it around even after the last key is released. But that is a project for another day. So let's give it a try. Now let's decrease a little bit the decay. Let's put the decay to the max and the attack to 0. Decreasing now the decay. Decreasing the sustain. And now the difference has become very noticeable. Let's increase the decay again. And now let's decrease the decay so we can notice the difference. Let's add some attack. Increase the decay a little bit more. Takes a long time to go down now. And of course, if we decrease the peak, we decrease the overall volume. Let's now try to use the envelope generator for something totally different. So far we have seen the envelope generator used to modify on the fly the amplitude of the output signal. But we can use the generator for many other things. For example, we can use it to control the frequency of a signal. Let's attach the ADSR control voltage to the FM input of the VCO and let's see what happens. Hey, isn't that cool? Well, this was a long video. We spent a lot of time going through the assembly of the ADSR module, and we went through a few design hiccups, which we solved promptly. In the next episode, expect something very different and very useful to add to our synth. Can you guess what? Write it in the comments. And also, don't forget to subscribe and to activate the notifications to avoid missing future episodes. And finally, I will leave you now to some music generated, of course, with the help of my synth. I'll see you soon, and happy experiments!